Hi, welcome to Geometry 2. Obviously there's a camera here. If you didn't take Geometry 1 with me last semester, I think about half of you did. I'm going to be filming every single lecture, so if you can't make it to class one day or you're ill or something, don't feel like you're missing anything. I will literally post this entire lecture on YouTube right after the fact, so hence the camera. How many did take Geometry 1 with me? Yeah. Okay. So about half of you. Have you looked at the syllabus at all? It's pretty bare bones, pretty straightforward. We'll be going through this textbook, Roads to Geometry, 3rd edition. You'll want to pick up a copy, or at least find a copy somewhere online, because I'll be assigning homework from it. And it's a pretty nice read. It's fairly easy to read, I think. It's not super dense like some math textbooks are. In some places it reads like a novel, really, so it's not that bad to read. We'll be going through that textbook. There's weekly homework assignments, there's 3 unit exams, and there's a final exam. The homework assignments will look like they did last semester, probably, I don't know, 4 problems or so each week. Fairly proofy, right? The idea in this class is to build skills writing proofs and developing these proofs. And I think the breakdown I went with these things is, I think 40% was the homework, 40% was the exams, and then 20 for the final. Don't quote me on that, but I'm pretty sure that's what I did. So the only real difference, if you took Geometry 1 last semester, the only real difference is that the exams will be once again in class, so scheduled in here at a particular time. And of course, we had those issues last semester where the take-home exams felt like just another homework assignment. I don't want to do that. I want to be able to put questions on there that aren't just write another proof, right? I want to ask you to define things or state theorems, stuff that you obviously, I can't test you on if it's an open book exam, right? that doesn't make any sense. So we will have in-person exams. If that's an issue for you, if actually physically coming to class in person is an issue for you, if you're immunocompromised or something, we can do that somewhere else. I can set up another room for you, but yeah. Any questions so far? Okay, I mean that's the structure of the class. If you didn't take Geometry 1 with me last semester, no big deal. I think it's officially a prerequisite for this class. There's other prerequisites too, like 317. Have you all taken 317? Yeah, okay, if you haven't, I don't care. I don't know why it's a prerequisite, to be honest. All I really care is that you've taken 201. Is that intro to proofs? That's 201? Yeah, so that you're familiar with what proofs are, how to write them. Maybe they require 317 because it means that you have more experience writing proofs coming into this class, but I'm fine with thinking of this class as sort of an introduction to actually writing proofs, as long as you're familiar with what they are. And yeah, if you haven't taken Geometry 1, that's fine. A lot of students last semester in Geometry 1 had only taken Geometry 2, which would be the situation you're in right now. The 2 classes are fairly standalone, so we should be fine in that regard. And I literally just taught in here last semester, and I can't remember for the life of me how to get that projector to go up, but that's okay, because I'll only ever use this board since the camera can only capture this board. And the more questions you ask me, the less math we'll do today, but you guys don't seem to have any questions. So, ask me something. Favorite color is blue, yes?
Is the grader the same?
I need to contact someone about that. I don't even know if we have a grader. If we don't, it'll be me. If we do, I'm hoping we can get Niall again, because Niall is fantastic, but yeah. Any other questions? Yes?
So exam will be in class on the whole?
They'll be in class. I think I put the dates on the syllabus, but they're tentative. We might change those. I think last semester I moved one by a week or something, but yeah. Yes?
Are homework assignments due Friday, like in class, or they do like Sunday night?
So again, I don't want anyone to ever feel like they have to come to class, so I will actually not be taking them from you by paper. You'll just submit them a PDF on campus, and yeah.
Cool.
And probably probably due Fridays is a good schedule, yeah. Obviously none this first week because we haven't done anything yet. All right, so let's get into it then. Let's just, we won't have a full class today, I promise, but we'll do a little bit. We'll talk about where we're going with this semester. So 1.1 in the textbook is just a little bit of brief history. You pretty much can't avoid talking about geometry without getting into some history because there's 2,000 years of it. It's one of the first big areas of mathematics. But not much to say about 1.1. It really just gets into some of the history of some of the big names behind geometry. So let's move straight on to 1.2, which is the axiomatic method. And this is one of our big goals this semester. Of course, what we'll be doing in this class is we're talking about Geometry 1 is all Euclidean geometry, the type of straight line geometry that you're used to. Geometry 2 is more dedicated to non-Euclidean geometry, spherical geometry, hyperbolic geometry, and so on. But even at the end of this class, you still won't be an expert in hyperbolic geometry because we're not devoting all of our time to that. And in fact, if you're going into, say, education or something, knowing a bunch of hyperbolic geometry, probably not the most useful thing in the world. It is fun, though. I am a geometer. My PhD is in geometry. And by the end of this class, you'll know more hyperbolic geometry than most people do. It's not unusual to find PhD-holding mathematicians that don't know anything at all about hyperbolic geometry. But what I hope we can get out of this class is sort of this idea of how math actually works. And this is the axiomatic method, how results are established and built up and whatnot. So I'll give you sort of a loose definition for the axiomatic method. The axiomatic method. So what is this? This is a way of demonstrating results in mathematics. And not really just strictly mathematics. This could apply to any scientific theory at all. But a way of demonstrating results in mathematics by establishing first a few axioms or primitive postulates that we accept as true. So by postulating certain primitive assumptions while all of the remaining results of the theory are obtained as logical consequences of these postulates. Right, so the second part of this, while the remaining results are obtained as logical consequences, that's what you usually think of when you write a proof, right? You start off with a statement, and you want to write down a series of logical implications that imply some other result, right? So you start off with something you say is true, and by writing a proof, you prove something else, and something else logically follows. The beginning part of this is where you start from, right? You have to start off with something that you accept as true. And these are things that we just believe in, we accept, we don't prove them or anything, we just state a list of axioms and we say these things are true, what can we prove now accepting these things as being true? This goes back a long way in terms of human history. This was developed by the ancient Greeks, really. Developed by ancient Greeks. I find a lot of math history really is sort of ethnocentric. It could have been some Indian mathematicians or Chinese mathematicians that were also doing this stuff, but I've never really heard about it. So I do believe that ancient Greeks were sort of the first to really care about axiomatic method. And one of the finest examples of this is, of course, the Elements published by Euclid, so Euclid's Elements. We talked about this a lot last semester in Geometry 2, forms the foundation of Euclidean geometry. This is 2,000 years ago, and he sort of was one of the first people to really produce a fine example of the axiomatic method. So, one of the earliest and best examples. Whereby he developed all of Euclidean geometry on just 5 axioms, 5 postulates. So developed Euclidean geometry. Sorry about the handwriting here, it's too low on the board. From 5 postulates. We also sort of ripped this to shreds last semester. He did it all wrong, but but for 2,000 years ago, it was pretty good. And it wasn't until about 200 years ago that people started to appreciate, hold on, we need way more than he's postulating, and he's assuming things that he doesn't write down as postulates. But still, 2,000 years ago, really, really good. All right, so what do I want to say here? I want to talk a little bit about axioms, but before I do that, let's just talk about language. So, if I say a word, or if I define something, well, let me not say define, but if I say a word, everyone has to understand what it means, right? So terms and statements. Terms and statements must be understood. Hence, we have to make definitions. For example, if I want to talk about triangles, I need to define what a triangle is so that we all agree on what a triangle actually is, right? So, the problem here is this leads to really a chain of definitions. Right, for example, let's define a triangle. A triangle is, define a triangle for me.
Three-sided polygon.
A triangle is a 3-sided polygon. I accept this. The problem is there's 2 other words in here. Polygon and sided. So we need to agree on what these words mean. So how would we say a side? A side is, what's a side?
the straight line
Cool, all right, and do I want it to be infinite, or I really just want a segment, right?
of some
So,
length,
yeah, we'll say a side is a straight line segment.
Yeah.
Cool. Well, now there's other words in here. Straight, we can talk about that. How about line segment? A line segment. All right, what's a line segment? I'm not even gonna bother. You start to get the point, right?
Sure.
This is gonna be an infinite chain of definitions. It's never gonna stop. And again, going back to Euclid's Elements, he didn't really appreciate this. He attempts to define everything. I think he gets down to a point, and he says a point is that which has no part or something. What does that mean? So again, it's not until recently, within the last 200 years, that people have started to appreciate that you can't just have an infinite chain of definitions. At some point, there have to be some words that we all just universally agree that we understand. For example, usually in geometry, a point is not defined. We all intuitively understand what a point is, but we're not going to attempt to write a definition. So this leads to an unending, or maybe not unending, maybe you'd come back eventually to your definitions would come back to triangles or something. So an unending or circular. Unending or circular chain of definitions. So that's a problem. So what do we do again? We accept some primitive terms that we leave undefined. So to solve this problem, we accept that some terms must remain undefined. And these are, in the axiomatic method, these would be our primitive or undefined terms. So primitive or undefined terms. Alright, so completely similarly, back to the axioms, when we're writing our string of logical implications, this is true, so this is true, so this is true, so this is true, we have to start from somewhere. It can't be an infinite chain, it can't be circular, so we have to start from somewhere, so we start with a list of basic axioms that we accept are true. Alright, so similarly, our chain of statements in a proof, these cannot be infinite or circular. And it must start somewhere. It must start from some truth. And so we accept certain fundamental truths in our system. So we accept certain so-called fundamental truths system. So these are statements that need no proof. And I'm really, there's an M dash over there, we'll overdo the M dashes today. But statements that need no proof. Things that are reasonable to accept, that you probably won't argue against. For example, one of Euclid's postulates is, okay, if I have 2 points, then there always exists a line passing through those 2 points. Right? That's not something that needs to be proven, it's just an accepted fact that yes, okay, if I have 2 points, there's always a line passing through them. And yeah, so these these fundamental truths that we accept, these are the so-called axioms or postulates of the system we're working with. So these are the axioms or postulates. "2,000 years ago, people sort of thought of axioms and postulates as being slightly different. They distinguished between them just a little bit. Today, we accept we just think of those as 2 separate words for the same thing, right? So, the fundamental truths we start with. Any questions so far? All right, so by the way, this is where we're going in this class, is we won't sort of do a whole bunch of hyperbolic geometry, because if you want to get really deep into hyperbolic geometry in one semester, you take what's called an analytic approach, where you can really delve straight into it. We're taking a so-called synthetic approach here, where we're going to build up hyperbolic geometry basically from scratch, from an axiomatic system. We'll start off with just a few axioms and build everything up from there. And while we won't get as deep into hyperbolic geometry because of that, hopefully you'll have an appreciation for just philosophically how math works and how we establish any field of mathematics. And trust me, everything you've ever done is based on just a set of simple axioms. So let's see, how long do we have? Only 25 minutes. Let's do an example of an axiomatic system. I'll give you some undefined terms. And I'm going to be very abstract here, because I want you to appreciate the fact that this really can be quite abstract. But usually your undefined terms would look like lines and points and stuff like that. Things that you have an appreciation for what they sort of mean already. But here we'll go with, my terms will be fees, foes, and belongs to. And so there's my primitive terms. Now I need a bunch of axioms. So axiom 1. There are exactly 3 fees. 3 distinct fees. I'll be very precise here. All right, so this is a universal fundamental truth. We don't have to prove it. I'm just telling you straight up, and we all believe it. If you don't believe it, by the way, you can just you can come up with a different axiom and come up with a completely different axiomatic system that might have completely different truths and results and whatnot. But there's exactly 3 distinct fees. Any two distinct fees belong to exactly 1 foe. Not all fees belong the same foe. And finally, we've got a fourth axiom that says any two distinct foes contain at least one phi that belongs to both. All right, so we have a whole bunch of axioms here, and I don't want to talk too much about them, but here's my question. And this isn't something I'm postulating, by the way. I want you to appreciate this. These are my 4 universal truths. I want to see, can we establish other things that must be true? All right, so here's our first sort of result in this axiomatic system. How many foes are there? And everything right now is very abstract. Everything's very abstract, but you might notice by the terminology, I'm talking about belongs to, and I'm sort of using or conflating this with contained in and so on. This feels set theoretic to me. Right? It feels to me, and this is what we're going to do, is we're going to build a model of this axiomatic system. And if you want to answer questions like how many foes are there, it'll often help to have a model in your mind. You might want to think of phis as being sort of elements of a set, and foes as being the sets itself. Right? And belongs to would then mean a set theoretic phi is an element of foe, right? It's an element of the set. So think about, I'll give you 5 minutes, think about this. How many foes are there in this system? Can we establish a result? So it turns out there's exactly 3. And I said we were going to build a model, but then I looked at the time. We'll put off models to the next class, but I want to prove this. I want to prove, without using a model, let's just try and prove this. I should have left myself a bit more space. I'm going to try and squeeze a proof into just this little area here. So here's my first theorem. My first theorem is not actually that there's exactly 3 foes. I'm going to prove that there's at least 3 foes. It is true that we can prove more than this, that there's exactly 3 foes, but for now, let's just prove that there's at least 3. And we'll go through our axioms here. I need to sort of do some sort of counting argument. So there, axiom one tells us that there are exactly 3 fees. And axiom 2 tells us that if I take any pairs of these elements, there's sort of exactly 1 foe corresponding to them, right? So axiom 2 tells us that that each pair of foes is on or in, I'll go with on, is on exactly, each pair of fees, my bad. Each pair of fees is on exactly 1 foe. And my claim is this. So now I'm going to invoke axiom 3. I'll draw a picture in a second to try and illustrate what I'm thinking of. But since all 3 fees cannot be on the same foe, this is axiom 3, by counting distinct pairs of fees, we have at least 3 foes. And I'm going to be honest with you, I'm not a big fan of this proof because everything is so abstract, this just feels a bit weird. But this is actually a legit proof. We're done at this point. But let me try and parse what I've written. And this is where models come into play. Everything's a bit easier with a model. So I have 3 fees. There's fee 1, there's fee 2, and here's fee 3. And that was axiom 1. What did axiom 2 say? Axiom 2 said if you choose any 2 distinct fees, they belong to exactly 1 foe, right? So if I choose those 2 fees, they belong to a foe, and I'm going to interpret a foe as sort of being this, this set that contains them. If I choose these 2 fees, those belong to a foe. And if I choose these 2 fees, those belong to a foe. Alright, so there's foe 2, and here's foe 3. Now what might be possible is that all these sets that I've drawn are actually the same set. Maybe it's all just one big set, right? So that's possible. But axioms 1 and 2 don't tell me that it couldn't possibly be the case that they're all just contained in one single foe, one single set. But axiom 3 comes in, right? Axiom 3 says that that's not possible. I can't have all 3 of my fees sort of living in the same foe, in the same set, if you think of it like that. So now you start counting distinct pairs, right? Because they can't all be in the same. So now I start counting how many distinct pairs of fees do I have? And the answer is 3. So I do have at least 3 foes corresponding to this situation. Yeah. And if you think about this, you'll realize that I actually have exactly 3 distinct pairs, and every single pair corresponds to one of these foes. So it's impossible to have 4. So our next theorem would be that there are exactly 3 fees. No, 3 foes, sorry. I'll leave the proof as an exercise to you. We won't prove it. Proof is an exercise. But the easiest way to proceed, and this is a very common method of proof in mathematics, is if you want to prove there's exactly n of something, exactly 3 in this case, prove that there must be at least 3, which is what we've done, and prove that there can't be more than 3. And then there must be exactly 3. So prove that there cannot be more than 3. Okay, and the way you do this is assume a fourth exists. And you'll arrive eventually at a contradiction. So I don't want to sort of end on this note, leaving you with this sort of with this taste in your mouth. I promise you, this class will not be this weird. We won't be talking about fees and foes. Everything will be lines and points and things that you have a nice handle on and can grasp. We'll talk about models next time. We'll build a lot of models for axiomatic systems, which I think is fun. And here I sort of gave you, this really is a model. Here's another model, and this is usually what I go to because I'm a geometer. I like lines and points. I would interpret fees as being just actual points, right? So there's phi 1, here's phi 2, and here's phi 3. Now we have foes, right? We have foes for every two points. There's a foe. And what does belongs to mean? What does it mean for two phis to belong to a foe? Well, I would interpret that as being endpoints of a line, right? So I have 3 points, and my foes are lines between them. And this is a legit model. If you interpret everything this way, you can look at the axioms and see that in this model, yeah, those axioms make sense. But we'll pick up here next time. We'll talk about models for axiomatic systems next time. So see you then.